Welcome. In this video, we finish Chapter 2 with the section 2C, Applications of Sets. We'll look at two big ideas, surveys and the principle of inclusion-exclusion. And this is it. This finishes Part 1, making sense of reasoning. Surveys. In a class of 25 students, suppose 10 play sports after school, and 14 enjoy chess. 5 neither play sports nor enjoy chess. So here's the question. How many students play sports and like chess? This question is a little tricky to answer, especially without a diagram, so it's very helpful to draw something like a Venn diagram that shows these groups as sets. And we see that the set of students who play sports after school can intersect the students who enjoy chess. At this point, I encourage you, actually take a few minutes and see if you can solve this problem. And then when you are ready to check your work, you can start it up again. Okay, give it a try. All right, we're back. Let's take a look at how we might do this. So 25 students altogether. So I think to myself, 25, that's like the universe. This is the rectangle outside of everything. And 5 students neither play sports nor enjoy chess. So I think that there are 5 kind of in the universe, but not within either of those circles. So I really know that there's 20 students among the two sets here. If I shade in both of those, that's 20 students there. Now, 10 of them play sports after school. So let me just focus on the 10 who play sports after school. I absolutely know that there's 10 there, so I'll draw 10 big 10. But like I said earlier, that 20, I'm keeping the 20 in the back of my mind. 20 is the two sets together. So I've shaded in something representing 10. So what has to remain is 10 here. So this 10 is the people who are in the chess group, but not in the sport group. Okay, I think I'm getting closer. Now let me erase that. And now let me turn my attention to the chess group. Remember that 14 people enjoy chess. So now I can say, oh, I have 10 accounted for already. What must remain is 4. So I need 14 altogether. So there we go. So 4 is my solution. There are 4 students that play sports and like chess. And just to complete the picture, if I'd like, I can also look at the sports group and say 10 play sports, and so there must be a 6 in this region. Here's another survey example. What do you like as a pet? People were surveyed, and they had to choose between skunk, rat, and hedgehog, of course. And these are the survey results. 20 like skunks, 10 like rats. Oh, and by the way, so looking at the picture, if I say 10 people said rats, that means that in this circle, there are represented 10 people. But I don't know how they break up. It might be 2, 3, 1, and 4. That would be one way that I could make 10. Or potentially, maybe I have 8 people there and 2 people there, and then it's possible I could have 0. All right. But somehow, the 10 people that like rats, they're split among those 4 regions. All right, continuing on. 30 like hedgehogs, 8 like skunks and rats, 15 like skunks and hedgehogs, 6 like rats and hedgehogs, 5 like all 3, and 4 like none. So how many people were surveyed? Oh, that's the question. How many people were surveyed? That's what we're really after. And this is a tricky problem because there's a lot of overlap, and I don't really know how things break down. But there's a good trick, is work from the inside out. Work from the most specific to the least specific. Basically, work up the list backwards. Say, look at the 4 first. 4 like none, so I know that I can put 4 people outside of all 3 circles. Now, working up from there. 5 like all 3, so I'm going to put a 5 right in the middle of everything. Those 5 people like skunks, rats, and hedgehogs. All right, moving up, 6 people like rats and hedgehogs. What region of the graph is that? That's this lens-shaped region here, the intersection of rats and hedgehogs. 6 people, 5 are accounted for already, so the 1 must go there. Now, 15 like skunks and hedgehogs. So I look for the region of the graph for those 15 people, and I see 5 are accounted for already. 10 remain. There we go. 8 like skunks and rats. So I highlight this region of the graph, and it looks like 5 are accounted for. I need 3 there. 30 like hedgehogs. Okay, we're in the outer circle, hedgehogs. 30 people altogether like the hedgehogs. Well, it looks like 16 are accounted for already, so 14 remains. 10 people like rats. Let's say it looks like I have 9, so 1 more there. 20 like skunks. What do I have so far? So far I have 18, which means I need 2 more. There we go. And like that, I've completed my picture. Now on to the question. How many people were surveyed? At this point, I really can just add up all the numbers and get my solution, which turns out to be 40. All right, so we were able to figure out the solution to this problem, and then that helps us answer maybe some other questions. So some follow-up questions might be, how many, whoops, how about how many, there we go, how many people like exactly 2 animals? Where are the people that like exactly 2? Do you see that? That's the 3, 10, and 1. Those are the people that like exactly 2 animals. So 14. There are 14 people that like exactly 2. How about how many people like hedgehogs, but not rats? So I look in the hedgehog circle, but I don't want anything that's also in my rat circle. So the 10 and the 14, so it looks like 24. There are 24 people that like hedgehogs, but not rats. Let's talk about the principle of inclusion-exclusion. Now, if I have 2 sets, A and B, the number of elements in A or B is the cardinality of A union B. I take the union of the 2 sets and then figure out the size of that thing. And there's a formula for this, this number, this A union B. It turns out the number of things in A or B is the number of things in A plus the number of things in B minus the number of things in A and B. Here's what it looks like sort of graphically. The number of things in A, I might draw this out like this. If I count every element that's in A, I'm taking the set A into account. All right, so I add up that number, and then I add the number of things in B. So I'm going to draw some more lines to represent I'm adding up all the things that are in B. But what's happened, I've overcounted, I've double counted this stuff in the middle. I counted it twice when I should have only counted it once. So I actually subtract out that quantity once, and that will leave me with the correct number that I want. Here's another way of looking at it. Suppose I actually draw dots to represent the elements in the different sets. So I don't know, maybe I have 3 elements there, 2, and then 4 elements outside there. And let's start counting out, well, first of all, just from looking at this, how many elements are in the union of A and B? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 things in A union B. But if I count the things in A, okay, 1, 2, 3, 4, 5, and then I count the things in B, 1, 2, 3, 4, 5, 6, you see, I don't get the right answer. The answer shouldn't be 5 plus 6. Clearly 9 is not 5 plus 6. I've overcounted. I've overcounted the 2. 5 plus 6 is 11, so I need to subtract off the 2. So subtract there, and now we have it. Now I have 9 circles without the overcounting. Here's how we might use this in a problem. Suppose 10 kids play sports, 14 like chess, and 4 do both. So maybe A represents the sports kids, B represents the chess kids, and you can see some kids do both. In fact, there's 4 in there. The question is, how many kids either play sports or like chess? I'm really after this union. How many do one or the other? And so, by following my principle of inclusion-exclusion formula, to get my answer, I take the number of kids who play sports, so that's 10, plus the number of kids who like chess, there's the 14, so I've done them individually, it's kind of like the 10 and the 14 there, but then I need to subtract off the number of kids that do both, the number of things in the intersection, 4. So 10 plus 14 minus 4. And the answer to that, 24 minus 4 is 20. So there's my solution. Here's another example, and I want to make a point. In this formula up on top for inclusion-exclusion, there are 4 numbers. 1, 2, 3, 4. It's possible different problems will give you 3 of those numbers, and once you know at least 3 of those numbers, you can always figure out what the 4th is. So here's an example of that. In this example, there are 30 students who are either English majors or active in the theater club. It's like that 30 represents the or, the together. I'll just write 30 right now. Now, 20 of these are English majors, so I'll put 20. This is my 20 right there. And 18 are active in the theater club. This is my 18. 18 are over there. And so here's the question. How many are both English majors and active in the theater club? I'm really looking for the intersection. That's what the unknown part here is. Well, I can figure out the intersection now just by working with the formula. 30 equals 20 plus 18 minus something that I'm not really sure. I'll call it x. We'll give it a variable name. So let's figure this out. 30 equals, now 20 plus 18 is 38. So 38 minus x. Now maybe you can just realize what x is right now. 30 equals 38 minus something. Well, of course I have to subtract off 8 to get back down to 30. But if you wanted to do a little algebra, I could add x to both sides. So 30 plus x equals 38. And then I could subtract 30 from both sides, and I get x equals 8. So there we go. 8 is our solution. There are 8 students who are both English majors and active in the theater club. You can do the principle of inclusion-exclusion with 3 sets, and there's our big formula for it. We won't really do problems with 3 sets, but I just wanted to show you because it's kind of interesting, and you can see how it extends the 2-set version. I start by adding all the individual sets. Here's everything in A, plus everything in B, plus everything in C. So I've added everything in A, plus everything in B, plus everything in C, but I've overcounted, right? You can see 3 regions where I've double counted, kind of the ends of the 3 leaves. And in the very middle, I've actually triple counted. Do you see how that region has been shaded 3 times? So I need to start subtracting in order to correct the overcounting that I've done. So here's what I do. I'll subtract off the stuff that's in A intersect B. So I'm subtracting off everything in this lens-shaped region. All right, give that the right color there. And I need to subtract off everything in A intersect C. A intersect C, I'll use yellow. A intersect C. So this lens-shaped region here, I'll subtract off all of those elements because I had overcounted before. And then I'll subtract off everything in B intersect C. B intersect C is this region here. So by subtracting off those 3 regions, I've corrected actually the ends of the leaves because now they're down to 1 count each, but I've actually overcorrected right in the center. Initially I had triple counted, but then when I subtract off 3, now I've taken them all in. So finally I need to add that region back in. And so we add A intersect B intersect C back into the middle to correct for it. So like I said, we're not really going to use this formula a lot. It's just kind of interesting and I wanted to show it off. Here is one example that does have 3 sets, and it uses some interesting thinking, so it's worth spending a little bit of time on it. Here's an example. A school has 3 clubs, math, reading, and theater. 60 students belong to at least 1 club. Well, first of all, what does that mean? 60 students belong to at least 1 club. That means that this entire region here, all within the 3 circles, that all adds up to 60. 30 students belong to exactly 1 club. What region of the graph is that? Those students that belong to exactly 1 club. Well, these are the students that belong to exactly the math club and only the math club. Here are the students that belong only to the reading club. And here are the students that belong only to the theater club. So the shaded region in red, that adds up to 30, the 30 students that belong to exactly 1 club. Now, 5 students belong to all 3 clubs. What region is that? That's the guy right in the middle, all 3 clubs. Now here's my question. How many students belong to exactly 2 clubs? And the exactly 2 region, that's this area here. I'll put my 3 question marks. So the area that remains, those are the students, that represents the students that belong to exactly 2 clubs. They can either belong to the math and the reading club, or the math and the theater club, or the reading and the theater club. Well, I can figure this out by using the fact that there are 60 students overall, and I'm going to take away the red shaded region, so minus 30, and then take away the blue shaded region in the middle, minus 5. And this should give us the answer. 60 minus 30 is 30, minus 5 is 25, and there's the solution to that problem. And then one last question. How many students belong to at least 2 clubs? So not exactly 2 clubs, but at least, which means either 2 or 3. They belong to 2 clubs or they belong to 3 clubs. And so this will be the answer I just made, 25. Those are the students that belong to exactly 2, plus the 5 students that belong to all 3. So either 2 clubs or 3 clubs. And the answer there is 30. And that brings us to the end of Inclusion, Exclusion, the end of the chapter, and the end of part 1.